In our previous video, we discussed the first type of intermolecular force, which are London dispersion forces, which are typically the same, or they're typically the weakest of the intermolecular forces. We're going to see some examples where that is not the case, but in general, they are the weakest. The second type of intermolecular force that we're going to discuss are called dipole-dipole forces. And hopefully you remember that when you talk about a dipole, you're talking about a compound that is a polar compound or a polar molecule. Okay, so when you have a polar molecule, let's just kind of review from yesterday. If a compound is polar, it has dipole-dipole intermolecular forces, and remember, it also still has London dispersion forces. So even when things are polar, you can still have those electrons more on one side than the other. So polar molecules have dipole-dipole intermolecular forces and London dispersion forces as well. And again, when things are polar, typically those are stronger than London dispersion forces, but again, not always. Okay, so with London dispersion forces, remember we had those instantaneous or those induced dipoles, but with polar molecules, we know that when the molecule is polar, we have that permanent partial negative charge and partial positive charge, like you can see right here, and that never changes as the electrons move around. Okay, so you have these permanent dipoles, and they're going to arrange themselves. They're going to be attracted to other molecules in such a way that the positive end of one molecule is going to be attracted to the negative end of another molecule, and the opposite is also true. Okay, now obviously I'm trying to draw this on a two-dimensional surface. Remember that obviously gases are traveling in 3 dimensions, so it's hard to kind of show behind, but it's the same concept of that the positive end of one polar molecule is attracted to the negative end of another molecule. Okay, and so yes, all polar molecules exhibit 2 types of intermolecular forces, London dispersion and dipole-dipole forces. Okay, so let's talk about an example here of this. It says the melting point of XeOF4, diagram E, so this one here, is greater than the melting point of XeO3F2. Okay, identify the types of intermolecular forces that the 2 substances have in common. Okay, so first of all, if you remember from previously when we talked about that molecule right there, that is a trigonal bipyramidal shape that the fluorines, the dipoles and the fluorines cancel out, and then the dipoles and the oxygens also cancel out. This is a non-polar molecule. Whereas here, you've got the lone pair on the central atom, you've got the oxygen up here. That one is definitely a polar molecule. Okay? So what is the type or types of intermolecular forces they have in common? Well, since this one here is nonpolar, the only intermolecular force it has is London dispersion forces. Whereas this one over here, so this one is just LDFs, whereas this one over here, certainly because it's polar, has dipole-dipole forces, but all polar molecules also have LDFs. So identify the types of intermolecular forces that they have in common. The only one they have in common is London dispersion forces. Okay, it doesn't say to explain it, so don't. Okay, and then they say explain the difference in the melting points based on the types and relative strengths of intermolecular forces. Okay, and they tell you that the melting point of XeOF4, which again, this one here, is greater than the melting point of XeO3F2. Okay, so why? So they just want to explain, they're telling you the answer, they just want you to explain why. Okay, and the why is because XeOF4 is polar, it not only has London dispersion forces, but it also has dipole-dipole intermolecular forces, which again are stronger than the London dispersion forces in XeO3F2. Okay, so it comes back to the fact that this one has the dipole-dipole forces and the XeO3F2 does not. Okay, so sometimes one thing that comes up is sometimes you'll be comparing a non-polar molecule such as this and a polar molecule, and you'll find that the nonpolar molecule has a greater boiling point than the polar one. Let me give you an example of that. Okay, for example, HCl has a boiling point of negative 121. Or sorry, that's incorrect. Let's go to Kelvin. HCl has a boiling point of 188 Kelvin. Cl2 has a boiling point of 238 Kelvin. Okay, we have to account for the difference in those boiling points based on the types of intermolecular forces that occur between them. Okay, and here's where you have to really start thinking a little bit and go, wait a minute, Cl2, absolutely, that bond is a nonpolar bond. Certainly Cl2 is nonpolar, and you're exactly right. HCl, of course, is polar. So Cl2, because it's nonpolar, only has London dispersion forces, whereas HCl, because it's polar, has dipole-dipole and London dispersion forces. So again, your thought process is, well, wait a minute, HCl has to have the higher boiling point because it not only has London dispersion forces, but it also has the typically stronger dipole-dipole forces. Yet, we see that with those boiling points, the higher the boiling point, the more energy it takes to break those molecules apart from each other. So how can Cl2 have a higher boiling point than HCl? And it does. And you have to come up with a reason why. Okay, and that means you have to go back to the thought process of what affects London dispersion forces. One of those things, certainly the surface area is not much difference between those two. You've got HCl and Cl2. Okay, surface area almost exactly the same. Okay, so what's the other thing that affects London dispersion forces? Is the size of the electron cloud. Okay, chlorine is what, number 17. So it has 34 electrons between the two of them. Where HCl, hydrogen only has 1, plus the 17 from chlorine. Cl2 has almost twice the size of the electron cloud that HCl does. Okay, and well, does that make the difference? It has to make the difference. It's the only thing that could explain why Cl2 has the higher boiling point than HCl does. Okay, so how would you account for that difference? I would say that Cl2 has the higher boiling point because even though HCl is polar and has dipole-dipole forces, the London dispersion forces in Cl2 are much stronger because they have to be, right? They have the higher boiling point. They have the LDFs in Cl2 must be way, way stronger than the LDFs in HCl because Cl2 has a much larger electron cloud and is therefore more polarizable, okay, resulting in clearly a higher boiling point than HCl. Okay, because on a test, if they ask you which one would you predict has the higher boiling point, of course you would say HCl. And how would you explain it? Just like how we explained this one up here. Well, HCl is polar, so it has dipole-dipole forces and London dispersion forces. But Cl2 only has London dispersion forces, so I would predict HCl is going to have a higher boiling point. But when they tell you that it doesn't have the higher boiling point, that's where the thinking part comes in, and you go, well, wait a minute. How can Cl2 be higher? And you don't say, this is wrong. Okay, it's not wrong. Okay, those are the actual boiling points of those two. So you have to come up with an explanation why. Since Cl2 only has London dispersion forces, it has to be something with London dispersion forces that make it have the higher boiling point. And again, Cl2 with more electrons, the larger electron cloud, more polarizable, has stronger LDFs than HCl that make up for that difference in their boiling point. Okay, and that's about as tricky as it gets between dipole-dipole and London dispersion forces. In general, you're going to see questions like this, where the one that has dipole-dipole forces is stronger, but when the molar mass of one is significantly greater than the other, like in this case, Cl2 has a molar mass of 71, this one is 36 point something, okay? That's a lot bigger molar mass, and so therefore, again, remember, don't use molar mass, but use it to think about it. that electron cloud in Cl2 has to be so much bigger than that of HCl's that those LDFs are going to end up being strong enough to be stronger than both of those put together for HCl.